Right, let's see if we're live. It looks like we are live. Fantastic. Got there in the end. Sorry, having a few technical issues. Technical issues now solved. Right, I'm going to spend the next 45 minutes or so trying to fumble through some Julia code. My main background is Python, but Julia is just too pretty for me to not use it. Expect lots of horrible mistakes, lots of hideous code, lots of fumbly nonsense, and going to give the saddle points challenge a go. If that doesn't take me an entire 45 minutes, we're going to give a go at rational numbers as well. But yeah, let's see how it goes, if it goes at all. Right, so saddle points. Let's have a look at this. So, instructions: detect a saddle point in a matrix. So we say you have a matrix. Oh, hello, John. Hello, Jonathan. We got there. Yep, we're live. We managed it. So where's my saddle points bit gone? I lost me train of thought already. So saddle point. So you have a matrix. It has a saddle point at row 2, column 1. Okay, it's called a saddle point because it's greater than equal to every element in its row and less than equal to every element in its column. The matrix has 0 or more saddle points. Our code should be able to provide the possibly empty list for all saddle points for any given matrix. The matrix can have a different number of rows and columns, non-square. Note you may be able to find other definitions of saddle point online, but we don't care about them. Cool. Right, let's just run the tests and see what happens. Let's see what the expectations are. Let's see what fails. Let's do some test-driven development. Let's try and get something that matches the outputs without being too cheaty. Can I identify a matrix has no saddle points? Okay, well that's an easy one, isn't it? So is you and just see if that passed that test. I know it's a bit of a cheeky one, but I could get the easy ones out of the way first. Okay, perfect. That works. Good. Okay, so let's think back to the instructions. Let's have a think about what the expectations are of this. Let's see if we can break this down into a few smaller functions. And then jam those functions together. So my initial thought here is, let's create a function that goes through the rows and tells me for each row which index has the largest or is equal to the largest element, and do something simple for columns. You might be able to turn it into a single function. I might just leave it as 2 for the moment because it's probably easier and quicker for me to think that through that way. So let's just pseudo this out a little bit. So we have a function called, we want row max, and we're going to give it the matrix. And let's have a think about how we're going to do this. So we want to maximum coordinates of each row. There's probably a function already that exists in Julia, like argmax or something, that does this. But it's not as fun just relying on things like that. It's much more fun to write your own. So let's think how we're going to do this. So return the coordinates of each row where element let's create an output. So rows can be output. Just going to empty list for a moment. So we want to loop through each row. So and we want to keep the index number of the row as well, because we're going to use that for our coordinates. So we can say I row in each row. Then. So we're going to go through each row, keeping track of which row it is with the index. Oh, quite an important thing there. Enumerate. So we actually keep the index with us. For I row, enumerate each row. What are we going to need to do? So we're going to need to get the maximum of that row. So max row equals maximum of the row. So that's going to give us enter is what I need. Then I suppose we're going to have to go through each element of that row and check if it's equal to the maximum. So we could do something simple as, or going to need coordinates again. So for j element, enumerate row. If element is equal to max row, push output the coordinates of I, j. Because we're saying if the element is equal to the maximum in the row, we want to add that coordinate of the row, which we're keeping track of. The I and the j into our outputs. And output. Wonderful. Okay, so let's just try. See what happens. What do I want? I want show row max 10. So hopefully, for each, when we run this, hopefully I will get an output for each row, the coordinates of the maximum of the element that's the maximum, the coordinates of the maximum element in that row, in each row. Let's have a look. Should fail all the tests still, so shouldn't worry about that. Okay, this is good. This is what I want to see. I want to see a vector of coordinates. So I'm going, and they all look fairly straightforward. And for each one, it's going to have the same ones each thing. Yeah, because it's going to go through every test. So particularly unhelpful. Let's see if we can figure out which test that's supposed to be. So this will be this one. 1, 1, 2, 1, and 3, 3 is not equal to 2, 1, but 2, 1 is there. Okay, so I feel like this is working. I feel like this is doing what I believe and what I expect it to do. So let's crack on and assume that I'm correct. And let's figure out the other part of it. So the next bit we know call minimums. So we've got the maximum in each row. So in this example, what I'm expected to return is 1, 1, because that's the maximum in that one. 2, 1, because that's the maximum in that one. And in this one, it would be 3, 3, because row 3, column 3 is the maximum. Okay, good. So what we then want to do is get the minimum for each column. So the minimum of column 1. the minimum of column 2, the minimum of column 3. And then all I need to do is iterate through everything and compare those that match. So any one where the maximum of the row is also the same as the minimum of the column, that must be a saddle point, I think, unless I've misunderstood the task. Mr. Yardware, good afternoon. So let's give it a go. Let's add the column minimum function. Column min m coordinates for each column. The element is equal to column. So this is basically going to do the same thing, do an end to that, so it's going to indent nicely. So output, I spelled function wrong. Is that what's going on here? It's very upsetting highlighting. I clearly mess something up. Doesn't matter. Let's just work through it. Equals u col col. Should really, for naming conventions, keep it the same way around. So J's is equal to the column and I is equal to the row, because otherwise I'm going to get myself confused later. I'm going to get it the wrong way around. So let's just keep them the same way around for the moment. Min col is equal to minimum of the col, and then for I, because we're going now row-wise, so it's going to be the ith element. Col if equal to col push output I sure and output end. So let's just do the same thing. Let's show row max. Let's show col min of m. Just makes it that doesn't error out. I haven't messed anything up hideously. If I can get through this out without some sort of runtime error, I'll be very happy. I've somehow passed 2 tests. I don't know how I've passed a second test there. I've somehow gained a test, but it's fine. So let's just see if this does what I expect. So in this first test is going to be it'd be good to know what the actual matrices that's been given in the first test. So what's the, can identify a single saddle point. So the matrix is the 987, 532, 667. So that's the same as this one, is it? 987, 532, yeah, okay. So we're expecting this one to be the saddle point. So that is row 2, column 1, so 2, 1. And we're expecting the row max to bring back 1, 1, 2, 1, 3, 3. So let's just check that. Our row max brings back 1, 1, 2, 1, 3, 3. Gosh, it almost looks like I know what I'm doing. And col min, not col max, col min should be bringing back 2, 1, 2, 2, 2, 3. 2, 1, 2, 2, 2, 3. Look at that. So now hopefully, this is the easy bit. Ooh, so Chromax, no, don't show Chromax. Rows, is that one? Cols, that's that one. And then with a little bit of magic, so we can say for I in rows, row in rows, col in cols, if row is equals col. We're expecting a list, aren't we? So we should really have an output here. Output is there, and that should really be output because that's just a bit cheeky otherwise. So as a row equal to col, we can say push output row. It doesn't really matter if we do row or col because they should be equal, so it should be fine. And output. Right. Cross our fingers. See what happens. Are we gonna? Do we have any predictions as to whether this works? I don't know if I can do predictions on this. I'm not going to try. But any predictions if I'm going to get a full 9 tests passed, or if there's I haven't looked at all the tests, so I don't know if there's some sort of edge case that I've not taken into account here. But I'm really hoping that this is just going to work. So I'm just going to go for it. Let's see. Run tests. How many do we fail? Look at that. Frickin' genius. There you go, that's quite easy. That's quite nice, quite a nice little challenge. It is magnificent, thank you. Now could that be cleaner? Probably. We could probably, can we turn this Romax into a single function with colmin? I don't think so. Is there a built-in function that already does this? Almost certainly. Argmin, argmax probably has some means of doing Cartesian coordinates. I haven't checked. But I like my way better. It's more fun this way. So let's submit it. Let's mark it as complete. Go on, why not? So that gives me my slightly more abstract exercise that I've given myself for the last half an hour, which I don't think I'll get done because this is apparently a hard one. That last one was a medium one. This one is a hard one, I think. I'm not going to go back and check. I'm happy just assuming it's hard. It might actually be medium, but this is attempting to implement a rational numbers type in Julia. Again, I think Julia has its own built-in rational numbers, but that's not really the point. The point is trying to build your own. So we'll give it a go. Let's see how bad I can fumble through this one. So, okay, instructions. Rational number is defined as the quotient of 2 integers a and b called the numerator and denominator respectively, where b does not equal 0. Note, okay, so this is one of the notes where it's like, well, technically, actually it can, but I think it's, for all intents and purposes for this exercise, they can't. So an absolute value of a rational number is the equivalent to the absolute of a over the absolute of b. Gotcha. Sum of 2 rational numbers is complicated. Gotcha. The difference is also complicated. I remember how to do multiplication of rational numbers, so that's easy enough. Just, yeah. Dividing. Okay, this is lots of log information. I'm going to assume I'm going to have to implement methods for all of this. So this is going to be a bit of a struggle. So let's start off and try. Let's work simply through this and see what happens. Okay, so first things first. Let's create a new struct because we want to create a new means of holding our new data type, and it's going to be called rational number. I assume. I haven't checked the tests. Should probably do the same thing as last time. Let's just delete that. Run tests. see what happens. See what errors we get so we know what we need to implement. Again, I could just look at the tests, but that feels like it's hard. Yeah, there we go. Rational number, fantastic. Okay, my assumption was correct. So create a struct called rational number. We want that really to be a real number. N, it's going to be some type, and it's going to be D. N. Now, I assume N and D have to be integers. Seems reasonable. So, but integers come in lots of shapes and sizes in Julia. We can have in64s and 32, so we could just say T needs to be an integer. And so that can be T. That can be T. There we go. Done. All right, let's run tests, see what happens. I'm obviously joking. That's never going to work. So we need to create a function for creating these rational numbers. That constructor is going to have to deal with the fact that if there's a 0 in the denominator, it's got to throw an error. Yeah, it's timed out because I haven't done anything. And I think I saw something as well that the implementation should always be reduced to the lowest terms. So, for example, 4 over 4 should reduce to 1 over 1. Okay, yeah. So it's going to have to greatest common divisor on construction. That's fine. Oh, look, it even tells you. So look at that. And reduced form of a rational number should be in standard form, so the denominator should always be positive. If a denominator with a negative integer is present, multiply both numerator and denominator by -1. Okay, so we can't have 3 over -4. 3 over -4 has to be reduced to -3 over 4. Seems straightforward enough. So let's create a constructor for a rational number. So we're going to do an external constructor because I don't understand internal constructors. That's just because of me, not because there's anything special about them. I just don't understand the difference. So we're going to create a function for rational numbers. N has to be a t, D has to be a t, where, oops, t is an integer. So what we're just saying there is when we construct this, N and T both have to be of some sort of integer type, but we don't particularly care which one. We'll let Julia handle the rest of it. So if the denominator is 0, we're going to do a little trick. We do denominator 0 and throw. This is my favorite. I don't know if it's a Julia trick or if it's a. I don't know where this trick comes from, but it's such an excellent little trick. I'll try and explain. Denominator cannot be 0. So this little single line trick basically says if D is 0, well, okay, this right hand side of the AND is always true. So it will always throw this argument, but it also has to require for the left hand side to be true. So what we could say, we could do this as if D is that, then throw argument error. Or we could just say D is equal to 0 and throw argument error. And so if D is true, that means they're both true, which means the argument error is thrown. Which I think is beautifully simple and horribly difficult to understand, but it makes it really nice for like one-lining error messages. So I'll just leave that one there. Okay, so we need to create a new divisor. We need to greatest common divisor, GCD. So we need to get a new divisor. It's going to be the greatest common denominator of N and D. Seems fairly straightforward. You know, we want it to be the greatest common divisor of the two. We then can turn D into dividing D by U D, and N is going to be dividing N by U D. So we've reduced the terms by the same amount, by the same ratio. I'm not a mathematician. I can't use terms correctly. Okay, so that should deal with our greatest common divisor issue. The other one is standard form. So if D is less than 0, D times equals -1, N times equals -1. So that just flips the signs. If the top is if the bottom is negative, then we want the bottom to be positive and the top negative. We don't really care what the top is; it can be whatever. Rational number. Oops. Of type T and D. Wonderful. So if you don't know in Julia, you don't need to use return as a. You can say. Probably should have said this earlier. You can say return, but you don't need to. If you don't specify return, it will return whatever the last item term in your function is, which is sort of like a functional programming paradigm, and I quite like it. It's one less word I have to type, which is nice. Julia itself isn't a functional language. It can be a functional language. It's not explicitly a functional language like Haskell or F# or anything, but I like to try and follow the functional paradigms because I think they're quite nice. Okay, so that gives us our rational number if we give it 2. But what if we're building a rational number with just 1? So say what is 4? 4 is a rational number, but we don't say 4/1. But we want the term for 4/1, if that makes sense. So let's create another function, another constructor, for if we just give it a single number. Number? No, number. There's T, where we don't want to give. We only want to deal with integers. We don't want to deal with floats. There's floating point numbers. It's not really a rational number, is it? Where T is of type integer. And then this should be straightforward. We should just be able to say, should just be able to call out another constructor, type T, and over 1. Sounds about right, doesn't it? Because what we're saying here is if we just give it a single number that is of type integer, then return this function I haven't run any of the tests for a while. I should probably run the tests and actually see if any of this is doing anything in getting towards our completion, or if it's just going to fail on me. It'd be interesting if it does fail. Oh, look at that. Okay, we are getting our way through some tests. So yeah, our rational number is a real number. Good to know. I don't know if the screen share is updated. Looks like it has. Yep. Rational number 0, 0 throws an argument error. Good. And some ordering. We apparently accidentally passed some tests. I don't think that we passed those tests for any particular reason other than nothing is equal to nothing. So let's see what we need to implement. Okay, so we need to implement a function for 0, which is sounds like a bit of a nightmare. I don't know if I want to do that. It's probably not too hard. So 0 and 1, 0 and 1, addition. Let's do addition. We'll come back to 0 and 1. Let's try and do some addition. So let's go back to instructions and figure out how we add rational numbers together. So we need to override the add function, and we'd say, okay, A is going to be a rational number, B is going to be a rational number, and we want that to be another rational number. Now, what do we need to do? Where's our addition? So the sum of two numbers, where R1 is A1 over B1 and R2 is A2 over B2, is R1 plus R2, yeah, which is A1 over B1 plus A2 over B2, yeah, okay, is equal to A1 times B2 plus A2 times B1. I'm trying to visualize that in my head, what that is. But that seems fairly straightforward enough. So our numerator is, because we're just constructing another rational number, so we can construct it by just doing a numerator. So A1 would be A dot n, so it's the numerator of A times the denominator of B, so B2, so B dot D, plus, plus the denominator of A2, so A dot D, times B dot n. Yeah, so that's our numerator. And our denominator is going to be, I'm losing, these words mean nothing to me at this point. Numerator, denominator, numerator. Looks like B1 over B2. Interesting. Oh, that's different. Sorry, I'm reading the wrong thing. So a numerator is A1 times B2 at A2 times B1. So AN times BD at AD times BN over B1 times B2. Okay, so that seems easy. So BD, BN, sorry, times BD. So we've overwritten the addition function, or it's not overwritten, but it's a better phrase for it, but we've created a new implementation of the add function for two rational numbers, and it returns a third rational number. Following the rules, so let's see if that works. Let's run our tests. Let's see if we're going in the right direction. Let's see if I remembered how to use base.add. I'm hoping so. It'll make my life a lot easier if it is. 4 tests passed, that's 1 test more. Let's see if that's right. Arithmetic, addition, excellent. So at least that bit passed. Now it looks like we failed some others. Okay, so why did we fail that one? So we have our addition of 1, 2 over minus 2, 3 has resulted in 1 over 6, which should be minus 1 over 6. So where have we gone wrong? Is that in our initial rational number declaration, or is this somewhere else? Have we messed this up somewhere else? Anyone in the chat who can tell me where I've got wrong? Because what's the other one? So yeah, we're somehow getting 7/6 when it should be minus 7/6. Curious. Okay, just for the moment, I'm going to try just doing this because I can't remember if Julia does times equals like I think it does. So I'm just going to do that and just see if that fixes it. D is d over d, n is n over nu d. I wonder if that's potentially messing it up as well, dividing it by itself, if itself is negative. Maybe. Let's try it again. Let's see what happens. Oh, no, that's going to fail. Whoopsie. Ah, my first error. It's doing so well. Let's see where this goes. Yeah, okay, so it's still failing. So I need to figure out why I'm getting a positive 1/6 when it should be negative 1/6. Why is it 1/6? Why is it not negative 1/6? I feel like all of that should be right. Let's just check my implementation of. Actually, you know what? You know what I was going to do? Just because I don't trust maths. I want to have that. Oops. And that. Actually, I feel like I've messed this up. I feel like this does not feel right. B1 times B. That. I don't think that's right. I think we should be multiplying the. Am I just. Oh! Idiot. Figured it out. Completely misread how this is working. I'm thinking A is numerator, B is denominator, not what I've been writing. My entire add function. I'm surprised my add function worked at all. With my complete fudge of that. Okay. So it should actually be, sorry, numerator times. Okay, by chance I got that right. So the denominator of B minus, no, plus the denominator, no, then A2, the numerator of B, yeah, by accident I got this, pure chance, and the denominator of A. If I followed the naming convention they had here, it would have been a lot easier for me to get a mistake. So that should be the denominator of A times the denominator, the bottom number of B. Let's run that. Let's see if that works. That fixes my addition. Fort has passed, but I think, yes, test 5 addition. Is there any addition things here? Subtraction, multiplication, exponentiation, division, absolute, reduction to lowest terms. Lowest terms, interesting. Oh, okay, yeah, some functions we haven't added. Wonderful. Okay, that was easy. Let's just try those reductions to lowest terms, because that actually looks incredibly simple. We want a function called numerator and a function, I'm going to guess, called denominator. Oh my god. At least it doesn't say millennium. The function numerator A is going to be a rational number. We just want to bring back A dot numerator. In fact, we could do that in one line, we don't need to just get rid of that. And numerator A dot D. See if that works. See if that's a quick win on some tests. Yes. There we go. Reduction to lowest terms. We got through that one. Test 32. Nice standard order of tests you want to go, and you want to go first, second, fifth, 32nd, 33rd. That's the standard order of testing that you do in Julia. Okay, we got addition. We should probably do subtraction, and then I'm going to do addition, subtraction, multiplication. I don't know if I'll maybe do division, and I might have to call it there depending on our time, but let's give it a go. So base to add, that was fairly straightforward. Now that I actually can learn to read, base dot minus A is going to be a rational number, B is going to be a rational number, do the same thing, rational number. We could do this as a slightly, in fact, let's do this one slightly different. So let's do this by calling it as a function instead of doing it all in one line. So if we do it like this, it's identical. It's just a slightly different way of typing. So your rational number, and numerator and denominator. God, that's such a horrible word. The more I say it, the worse I get at saying it. So the difference should be fairly straightforward. So R1 minus R2 is, so A is the numerator, B is the denominator, not the other way around. So our numerator is going to be A dot numerator times the B dot denominator minus the A dot denominator. No, I'm going to get this. It's the B dot numerator times A dot denominator, and all that is going to be over same thing, B1 times B2, so A dot D times B dot D. This is a great argument for not just using letters, because this is I mean, look at that. That's utterly unreadable. Julia allows. I could have. Yeah, we could have done some beautiful Unicode stuff, but I haven't. So let's see if that works. Let's see if our subtraction works. It feels like it's fairly straightforward. So let's give it a go. Look at that. Rattling through these tests now. So subtraction, that works. Multiplication is an easy one. So we're going to go back to the single line way of doing it, because it just looks better. Rational, no, rational. B is going to be rational. all going to be a rational number. Exciting, right? Excellent, no problem, Jabal. Thank you for being here. What are we doing? Multiplication. Let's have a look. How do you multiplication? Multiplication, if I remember, you just multiply the terms. If that's it's just numerators multiplied on the top and the denominators multiplied on the bottom. A1 times A2 over B1 times B2, so easy enough. So A dot n times B dot n, and that's going to be over A dot D times B dot D. I'm just going to go straight on to assuming I'm right and do division as well. Division, we have A is a rational number, B is a rational number, and that's going to be all a rational number. And division, this is where I go back to high school maths, is essentially just crisscross multiplication. So it's going to be the numerator of A times the denominator of B, and the denominator of A times the numerator of B. I could literally read it here, inches to the right of where I'm typing, but I'm not going to. I'm going to be brave. I'm going to be a brave boy. I'm just going to assume that I'm right, and we'll find out in a minute that I'm not. So let's see if we can bring that to 8 tests passed. 9. Oh, that's even one more than I thought. Oh, we've somehow managed to do exponentiation as well. Interesting. Not entirely certain how we managed that one. But I guess we'll take it. Oh, it's where they're all the same. Great. Okay, so we've got 9 tests passed, 21 to go. So I feel like I'm going to have to do these 1 and 0 elements because they've just been staring at me. Absolute value is such an easy one though. And showing a rational number. Let's do showing rational numbers. That feels like a really nice one to do. Because it's such a cool little thing to do. So we're going to do overwrite the base.show. Now base.show needs an IO. And then our element is going to be a rational number. I think that's what base.show requires. I could look it up, but I'm fairly confident that's right. Let's do this as a, and all we're going to do is we're going to write to the IO. So we're going to say, okay, whatever the IO is, whether it's print or show or whatever it is, write to it this lovely output, and we just want, as they say, the numerator 2 slashes denominator. So that's easy enough, isn't it? So let's do $sign a dot numerator over $sign b dot denominator. Oops. Feels like that should work. Let's give it a go. See if we can get some more test pass. It's the most exciting bit, just watching the tests. Hey, look at that. So Exercism is a great platform. You can sort of like iterate yourself through these tests, and these tests sort of the simpler problems are just like, you know, did you get it right? These more complex ones get you thinking a little bit more programmatically, in the sense of, okay, how many different things do I need to implement from like the random donkey struct that I've created? So, okay, yeah, think about implementing plus, minus, multiplication, division. What happens when people print it? You know, what's the view? What's it supposed to look like? You know, it's all these little things that, there we go, look, it works just great. Okay, fine, I've put it off. Let's do these 1, 0 element things. Let's figure out what it is I need to do for these. So, what do we need? So we need to override the base.0, don't we? We need to do base.0, and we need to do base.1. So the way these functions work is you give them a type. So you say, okay, base.0 integer, and it will give you return a 0 of type integer. Or you say 1, it will return a 1 of type float. You know, if we say base.0 float 65, it's an interesting one, float 64, it will just return a 0 of type float 64. So we need to implement some funky way of getting our rational number type in. So first things first, is we can use the double colon thing to say what the type is. And it's not going to be a rational number, because that's an instance of a rational number. What we want is the type rational number. So we can say type rational number. Now, a rational number can be of any sort of integer. So it can be int 64, int 32, int 8, or generic integer. So we also have to take that into account, which is why I'm trying to avoid doing this, because it's all sort of nested curly braces and it's very easy to get this wrong. So, okay, so we need to take into account where t is an integer. So is that everything on the left-hand side that I need there? So we're saying base 0, we want to create a new method or a new function that when we have the type rational number of itself type t, of taking parameters t, where t is an integer, so our int type rational number I think that sounds about right. What we need to return is a rational number of type t. Zero, 0. Is that right? No, it can't be 0, 0. 0, 1. I think that works. No, because it depends on what the type is. So that would need to be, or is that unnecessary? Am I overcomplicating it? Does anyone in the chat know that I'm making a pig's ear overcomplicated version of this? Because I don't. Let's try it without. Let's see what happens if I do it without. See if that passes. If that passes, happy days. If it doesn't, I think I know where it's from. Oh, yep. Oh, yep, sorry. Get rid of that first. Let's try that. Let's try it again. Looks like I don't need it. Perfect. Now the great thing is, I'm just going to make a load of extra white space so we can see what we're doing. The great thing is this base 0 function is basically identical to what we want to do with the base 1 function. There. Nope. Copy. Paste. And all we have to do is say base 1. And instead of being 0 over 1, it needs to be 1 over 1. Easy, right? Let's give it a go. Test passed. Test passed. Look at that. Now we've just got exponentiation, multiplying it by itself. absolute values are easy enough. We can do that one. Base.abs a is a rational number. We can just say is a rational number. Abs a.n abs d. So we just say, okay, the absolute of a rational number is just the absolute of the numerator of the absolute of the denominator. So we should be able to just smash that one out. Look at that. Don't go away error, that's an upsetting error. But it looks like we just have, the only things left are ordering. God, this went through a lot quicker than I thought it was going to. Didn't think I was going to get through as much of this as I have. Let's see. Let's what are these ordering ones? So whether they equal each other, whether it doesn't equal, whether it's greater than or equal to. These feel fairly straightforward. I just don't know if okay, so we should be able to just, let's quickly do the equals, because that's a fairly important one. Is are two rational numbers equal? Just a dot n equals b dot n, and a dot d equals b dot d. So are the numerators the same, and are the denominators the same? Should work. If this crashes, very upset, because this is going to be one of my last ones I'm going to try and get through. Looks like oh, okay. It's not whether the two are the same. It's whether comparing it to a float. Okay, I'm not going to bother with that one then. Can I just get this exponentiation one? So let's have a look. Exponentiation. I know that's not the word. It looks like it's this one is we need to do to a real floating point number x is the quotient a to the x to the b to the x, which is a real number. What? Am I just misreading this? What test are we failing? Let's go back. Oh, sorry, understood. It's a real number to the power of a rational number, not the other way around. Okay, understood. Exponentiation of a rational number, a to the x over b to the x. I feel like I'm missing something here. It's a rational. Oh, it's this one down here. Sorry, I keep seeing the word root and I'm thinking doing square roots and stuff, but no, it's explanation of a real number to a rational number is x to the power of a over b, yep, which is root. So the square root, not square root, the root of a, b, where root pq is the qth root of p. Okay, so we can do roots through 1 over the power of 1 over something. So something being to the power of 1 over 2 is the square root, and something to the power of 1 over 3 is the cube root. So we can use that to sort of fudge our way through that one. So base dot exponent is nope. That, thank you. A is going to be a real, B is going to be a rational number. So that is going to be, let's just cast this to floats just to make sure everything works nicely. A to the power of, so the numerator, right? So b dot n. And this, yes, it probably is very low. I'm not facing the microphone and I'm mumbling to myself, so I apologize for that one. I could probably just speak louder. Hopefully if I just point my head in the direction of the mic, we actually get something. In fact, I want to put the chat over there. That probably makes it easier because then I can actually chat and see it at the same time. So this can be the last bit I'm going to do, and then that will be me done. So let's just get my head. So it's the qth root pq. So then that will be here be. So it's the power of 1 over the denominator. Let's give it a go. I've probably broken it. I'll probably get lots of errors, and that will just have to be how I end today. Oh, look at that. We've just got ordering left. Beautiful. Right, so I think that's it for me today. I appreciate you all coming out. If anyone's got any questions for me before I go, now's your time. But other than that, I'll give you a minute or two. But other than that, I've really appreciated my time to getting to play on the Exercism channel. Might see if I can do some more next week or later in the month. No, just getting a lovely thank you, Mr. Megakek, or Mrs. Megakek, or Miss Megakek, or none of the above. Good to see everyone out. Right. With that in mind, have a good evening all, and thanks for watching.